Alright, you are welcome to this week's class, HPHY209. So this is the fourth lecture. The course title is Elements of Modern Physics. So today we talk about Compton Effect. Compton Effect. Okay. So if in the last class we talked about photoelectric effect. So we had light or photon, striking an electron. So what happened in photoelectric effect was that the photon knocks out the electron, in the metal. So this electron is in the metal, and the photon has sufficient frequency. We call that frequency the threshold frequency. So we call it the threshold frequency. So in the case of photoelectric effect, so the photon knocks out the electron from the atom. So that is case one of what can happen if a photon interacts with an electron. So that is case one. Case one is the photoelectric effect. Now case two is the photon interacts with the electron, but it gets absorbed. So the electron absorbs the photon. So in this case, the electron will move from its initial energy state to a higher energy state. So the electron probably was at this energy level, E0, or let me say EI. It will now jump to EF, a higher energy state, because it has absorbed energy. It has absorbed photon. So the photon will give the electron energy. Now, case 3 is what we want to discuss today. And it involves the case whereby the photon interacts with the electron, but the photon is not absorbed, as in this second case. Also, the electron is not knocked out, as in the case of photoelectric effects. So in this case, this is before the interaction. So before interaction. Then after the interaction, we find that this photon, so let me use another color. So we find this photon changing direction. So this is the original direction. So this angle between the original direction of the photon and the final direction of the photon, we call that angle the scattering angle. Scattering angle. Then the electron also gets recoiled. So the electron moves in maybe this direction, so it gets recoiled. So this angle phi, we call it the recoil angle. Recoil angle. So in this case, the electron is not knocked out by the photon energy, and also the photon is not absorbed by the electron. So the photon continues its journey after interacting with the electron, but there is a change in wavelength. So if the original wavelength of the photon is lambda 1, the final photon is lambda 2. So there's a difference between lambda 1 and lambda 2. Between the original wavelength of the photon and the final wavelength of the photon. So there's a difference. So that difference is what we refer to as the Compton effect. Compton effect. So if there is no change in wavelength, then there's no Compton effect. But the fact that we have a change in wavelength, that is what we refer to as Compton effect. And this effect is one of the experiments or the phenomena which demonstrates the particle nature of light, the particle nature of the photon. So it demonstrates that the photon has particle properties as well as wave property. We'll talk about that later. So Compton, there's a derived formula which relates the final photon with the initial or original photon. So it says there's a change in wavelength. So the final photon is lambda 2 equals the lambda 1, which is the original wavelength, plus Planck's constant over the rest mass of the particle that scatters the photon. So here we are using electron. So in this case, this will be the mass of an electron. We can also use another charged particle. For example, instead of using electron, we can use proton. But in the original experiment, electron was used. So into bracket 1 minus cos theta, and theta is the scattering angle. So this theta, so it's called the scattering angle. Yeah, this is a theta, it's called the scattering angle. So let's call this equation 1. So the shift, the wavelength shift, is actually what is referred to as the Compton effect, because this delta lambda is greater than 0. If it is equal to 0, then there is no Compton effect. So usually it is greater than, so when it is greater than 0, that is when we have Compton effect. So you should be familiar with these constants now. H is Planck's constant and c is the speed of light. So this m0 is the rest mass of the particle. In this case, we are using electron, so it will be rest mass of the electron. All right, now, so please take note of this equation 1, so you can. Okay. Now, what are the values the change in wavelength can take? Okay, we said it must be greater than 0 for us to have Compton effect. So what are the range of values it can take? Now we have to start from the range of values cos phi can take, cos theta can take. So if theta ranges from 0 up to 180 degrees, so if it ranges from 0 up to 180 degrees, so what will be cos 0? So cos 0 is 1. And what about cos 180? Cos 180 is minus 1. So the values theta, cos theta can take, so cos theta can take values from minus 1 up to 1. So minus 1 up to 1. So these are the range of values cos theta can take. So we chose this 0 to 180. It means we can have, this is the original direction of the photon. The photon can continue in that direction after interacting with the electron. In that case, there is no scattering angle, so theta will be 0. And of course, the photon can, so let me use another color. The photon can get scattered at maybe 20 degrees, at 30 degrees, 40, 45, up to 90 degrees, then up to 180 degrees. And this can be scattered back, it can be reflected back by the charged particle, which is the electron or proton. So in this case, we're using electron. So the maximum angle can be is 180 degrees. So the range of values for theta is between 0 to 180 degrees. So and the range of values for cos theta will be between minus 1 and 1. So in that case, what will be the range of values for 1 minus cos theta? So this will be 1 minus 1, that will be 2. So that will be 2. So that 1 minus cos theta can have value between 2 and then 1 minus 1, 0. Okay, so 0. So it's between, so the range of values, is between 0 and 2. So between 0 and 2. So those are the range of values that 1 minus cos theta can have. Okay, so it means the maximum. So okay, before I explain this constant, this h over m naught c, I said is a constant. It's a constant because h is Planck's constant, is a constant. It is 6.626 times 10 to the power minus 34 joules second. Speed of light is 3 times 10 to the power 8 approximately meters per second. And this rest mass for the electron is approximately 9.11 times 10 to the power minus 31 kilograms. So that is the approximate value of the rest mass of an electron. So if you take out your calculator and you evaluate this, so you have 6.626 times 10 raised to the power minus 34 divided by 9.11 times 10 raised to the power minus 31, then times 3 times 10 raised to the power 8. So we get 2.4244. So 2.4244 times 10. So let me use 2.424 times 10 raised to the power minus 12 meters. Okay, so 10 raised to the power minus 12 meters. 2.424 times 10 minus 12. So this minus 12, it has 1 picometer. So we can write this as 2.424 picometer. Or we can also write, because 1 picometer is 1 times 10 raised to the power minus 12 meters. Or we can write it in nanometer. So that will be 0.0024 nanometer. Recall that nanometer is 1 times 10 raised to the power minus 9. So we can use any of these for this constant. Now, so this constant, we call it, there's a name we call it. So we call it the Compton wavelength. Compton wavelength. Compton wavelength. So we denote it as lambda c. So for the electron, okay, for the electron, it is because the reason why I said for the electron is because we use rest mass of the electron here, 9.11 times 10 to the power minus 31. So for the electron, this lambda e is 2.424 picometer or 0.0024 nanometer. So for the electron. For the proton, you can easily calculate. All you need to change is this mass. You change this to the rest mass of the of proton. So we know this this Compton wavelength now. So from this equation 1, which is the final, which shows the final wavelength of the photon. So we can now determine the maximum value it can take. So the max, so lambda 2, so we have lambda 2 equals lambda 1 plus all these constants HPHY209, that is lambda c. So lambda c. So the maximum, the range of value 1 minus cos theta can take is between 0. So it means it can be 0. That's the lowest value. So if it is 0, it means lambda 2 equals lambda 1. In that case, no Compton effect. No Compton effect. Now the maximum value it can take is, we said 2. 1 minus cos theta is 2. So the maximum is lambda c multiplied by 2. So that will be lambda 2 minus lambda 1 plus, lambda 2 equals lambda 1 plus 2 lambda c. Or we can say delta lambda. Delta lambda is the change in wavelength. Lambda 2 which is what, 2 lambda c. So delta lambda can be 2 lambda c. Delta lambda, this is the maximum, and the minimum is 0. But if it is 0, then there is no Compton wavelength. So the value, so anytime you are solving a problem of photoelectric effect, your answer should be between 0 and 2 multiplied by the Compton wavelength. If it is above this, then you should know that something is wrong with your calculation. Okay, so let's take an example. All right, so this example, X-rays of wavelength 2.0 angstrom are scattered from a carbon block. The scattered photons are observed at right angles to the direction of the incident beam. Calculate the wavelength of the scattered photon. So we have to calculate lambda 2. So from this equation 1, that's the Compton wavelength Compton equation. Okay, so we use the equation lambda 2 equals lambda 1 plus HPHY209, 1 minus cos theta. We have already calculated this HPHY209 for the electron. Okay, so and we got so we can write this equation as lambda 2 equals lambda 1 plus lambda c or lambda e into bracket 1 minus cos theta. So we are told that X-rays of wavelength 2.0 angstrom. So the original wavelength is 2.0 angstrom. Okay, 2.0 angstrom. So we can easily convert this to meters. And we are told that the scattered photons are observed at right angles. Right angles means the angle is 90 degrees to the direction of the incident beam. Okay, so we can easily calculate. So our lambda C or lambda E is 2.424 times 10 to the minus 12. So 2.424 times 10 raised to the power minus 12 meters. So in this case, lambda 2 equals lambda 1. So lambda 1 is 2.0 angstrom. We convert to meters, so that is minus 10 meters. Then plus lambda E, which is 2.424 times 10 to the power minus 12 meters. Okay, then into bracket 1 minus cos 90 degrees. So in this case, we have lambda 2 equals 2.0 times 10 to the power minus 10 meters. Then plus, so what is cos 90 degrees? So you can take your calculator and evaluate cos 90 degrees. So you get 0. So 1 minus 0, so that will be 1. And 1 minus 0, yeah, that will give you 1. So in this case, we have just 2.424 times 10 to the power minus 12 meters multiplied by 1. Let me remove these dots. Okay, so you now have lambda 2 equals, so you sum these two, so you have 2.0 times 10 to the power minus 10, then plus 2.424 plus 2.424 times 10 raised to the power minus 12. So you have 2.024 times 10 to the power minus 10. So 2.024 times 10 to the power minus 10. Right, let me check again. Yeah, times 10 to the power minus 10. So meters. So this is the change. This is the final wavelength of the scattered photon. So calculate the wavelength. So this is the wavelength of the scattered photon. So therefore, the wavelength of the scattered photon is 2.024 times 10 minus 10 meters, or 2.024 angstrom. Okay, so anyone is allowed. All right, so let's take another example. So example 2. So the question is, you use 0.124 nanometer X-ray photons in a Compton scattering experiment. At what angle is the wavelength of the scattered X-rays 1% longer than that of the incident X-rays? So you need to properly interpret this question before you attempt to solve it. So the question says, when you use 0.1, so the original wavelength, so lambda 1 is 0.124 nanometer. That's the original wavelength, lambda 1. So the question is now asking us to calculate the scattering angle. So that is, at what angle is the wavelength of the scattered X-ray 1% longer? So the difference between the final X-ray and the initial final wavelength of the X-ray and the initial wavelength of the X-ray is 1.0% of the original of lambda 1. So the change in wavelength, so they say, is 1% longer. So if you find the difference between the final and the initial, you'll find that the final is 1% longer than the initial. So the change in wavelength is 1% of lambda 1. So 1% of lambda 1 will be 1% means 1 divided by 100. multiplied by lambda 1, which is 0.124 nanometer. Okay, so you divide 0.124 nanometer by 100, so you get 0.00124 nanometer. Okay, so and we can easily convert this to meters, so that would be 1.24 times 10 raised by nanometer is -9, but there is another -3 here. Okay, so -9 and -3, that will be -12, so that will be -12 meters. So that will be the change in wavelength. Now, from our formula, recall that our formula for the Compton scattering is lambda 2 equals lambda 1 plus lambda c into bracket 1 minus cos phi. Our goal is to find this phi. So what we do, cos theta. So our goal is to find theta. So we make theta the subject of the formula. So how do we do that? So we can say from this equation can be written as delta lambda, which is lambda 2. So that lambda is lambda 2 minus lambda 1 equals lambda c into bracket 1 minus cos theta. Okay, so delta lambda is lambda c into bracket 1 minus cos theta. So we can make, so our goal is to find cos theta, right? So we can say cos 1 minus cos theta equals delta lambda divided by lambda c. Delta lambda divided by lambda c. So in that case, we can also make theta the subject of the formula. So theta, cos theta will be 1 minus delta lambda divided by lambda c. Okay, so all you need to do is you take this cos theta to the right hand side, so to be positive, then you take this to this left hand side, then it will be minus delta lambda. So then you now make so let's first evaluate this before we evaluate theta. So cos theta will be 1 minus, what is our delta lambda? Our delta lambda, we got it to be 1.24. so here, let me use another color. So this is our delta lambda, and the value is 1.24 times 10 power minus 12. So we have 1.24 times 10 power minus 12 meters, then divided by lambda c, that's the Compton wavelength. So we're going to use this, the Compton wavelength we calculated here. So since this is also for the electron, so lambda c, so that is 2.424 picometer. So 2.424 picometer, which is 2.424 times 10 power minus 12 meters. So if we evaluate this, then we get, so let's bring a calculator. So get 1 minus 1.24 times 10 power minus 12 divided by 2.424 times 10 power minus 12. So we have 4.884 times 10 power minus 1. So 4.884 times 10 power minus 1, which can be written as 0.4884, I believe. 488, yeah, 4. So 4884. Then we now make theta the subject of formula. So we say we take the arc cos of 0.4884. So what is the arc cos of 0.4884? Okay, so let's take arc cos of 0.884. So let's clear the screen. So arc cos of 0.4884. So that will give us 60.76. So theta equals 60.76 degrees. So this is the scattering angle we are asked to calculate. All right. So next, before I stop, let me quickly talk about wave particle duality. So wave particle duality. All right, so what is the wave particle duality? So this is a phenomenon which explains explains that light has both wave and particle properties. Okay, well, okay, I will talk about that later. So if we know that light has wave properties, so it can undergo reflection, refraction, diffraction, interference, and so on. For example, if we take a source of light, so let's say this is a source of light, so it will send radiation waves, send out waves. So how do we know that? So if you put some slits here and there's a screen here, so there's a screen at this side. So this light, so when it sends plane waves, okay, when the waves get to this edge, so they will diffract. So we have something like this, and for this as well. So this will be sent out up to when they get to this point. Now what will you observe on this screen? You observe light and dark spots, light and dark spots. Okay, that is what will be observed on the screen. What do we mean by light and dark spots? So for example, so let me use this. So we have light here, dark, light, dark, light, dark, light. So this is what we observe. Okay, so why do we have light and dark spots on this screen? Because sometimes these waves, they will combine constructively. So when we have constructive interference, then we have the light spots. Okay, so in this case, they just add up together to boost the wave. But we can also have destructive interference, whereby the waves cancel each other out. So when they cancel each other out, then we have the dark spots. Okay, so this shows that the light is a wave. So it undergoes this wave phenomena. But the experiment of the photoelectric effect and as well as the Compton effect demonstrates that light has particle properties, a particle. So if you combine these two, then we talk about the wave particle duality of light. So that light can behave as a wave and it can also behave as a particle. But light cannot exhibit these two different phenomena at the same time. So you can carry out an experiment that shows that light has wave properties, and you can also carry out another experiment which shows that light has particle properties. But you cannot demonstrate that light has the two properties in a single experiment. Okay, so that is what wave particle duality of light is about. So this concept is not peculiar to light alone. Electrons as well have these properties. So an electron can behave as a wave, and it can also behave as a particle. So in some cases it will be a wave, and in some cases it will be a particle. So this wave particle duality is a phenomenon that is common to electromagnetic photons as well as particles. Okay, so as well as particles, so electron, proton, and so on and so on. So they also exhibit this phenomenon of having wave property as well as particle properties. Okay, so this is where we stop today. But before I go, I will give you an assignment. So assignments. So this assignment you will submit next week Saturday, because next Saturday will be physical class. So you submit on 30th September. So to be submitted on 30 September 2023. So you submit this assignment. So the assignment is a simple one. So you explain pair production and pair annihilation. Alright, so you submit next Saturday. Okay, so this is where we stop today. So see you next time.